Good morning and welcome to 2017 AP Chemistry FRQ walkthrough for the question. Question 5 starts with a lengthy lead-in that I haven't replicated here, but starts with the equation for the combustion of propanol. It says, a student performs an experiment to determine the enthalpy of combustion of 2-propanol, C3H7OH liquid, which combusts in oxygen according to the equation above. The student heats a sample of water by burning some of the propanol. That is an alcohol burner, as represented below. The alcohol burner uses a wick to draw the liquid to the flame. The mass of the propanol combusted is determined by weighing the alcohol burner before and after the combustion. Data from the experiment is given in the table, and that's actually very important. But I want to draw your attention to something here. They give you a lot of background information, a lot of noise. Pause, set it aside. Yes, it's useful. Yes, it makes sense. But it isn't particularly necessary to solve the problem. It's good background, helps set the scene, but it isn't the meat and bones. Data tables presented below. A. Calculate the magnitude of heat energy in kilojoules absorbed by the water. Assume that the energy released from the combustion is completely transferred from the water. Now, I look at this drawing and I go, okay, there's no way in heck all that energy is going to be absorbed by the water. It's an open flame. There's plenty of places for it to go, but we're going to make an assumption here. And it's asking about the water. So we have water. It changes temperature. We have a specific heat. That makes me think MCAT, or as more often is said, Q equals MC delta T, which is an equation on your equation sheet. It's also the equation for heat transfer or energy absorbed, or however you want to phrase that. But it is the single most useful equation for this. Whenever I hear heat or transfer or change in temperature of a substance, especially if I see a specific heat, this is the equation I think of. And I have got all of that information. It asks for the answer in kilojoules, so we got to be very careful about that. But Q is your heat, or the amount of heat energy. M is the mass. In this case, it's the mass of the water, not of the propanol. Okay? We're talking about the water. We care about the water. The mass we use is of the water. C is your specific heat. For water, it's 4.18 joules per gram degrees Celsius. And then T, delta T, is your change in temperature. Remember, delta T is always T final minus T initial, or in this case 51.1, which is where we ended, minus the 22.0. And that's going to be in degrees Celsius. Check my units. The degrees Celsius and the degrees Celsius cancel out. The grams and the grams are going to cancel out, leave me with joules. I multiply all those numbers out, and I should get 15,200 joules. But I'm not done. It asks for my answer in kilojoules. If you prefer, you can just move the decimal, 1, 2, 3, or you can do a unit conversion where you say 1,000 joules is 1 kilojoule. But I'm just going to move my decimal 3 spots over from regular to kilo. So that is 15.2 kilojoules. And there's your answer. B then continues on. It says, based on the experimental data, if 1 mole of propanol is combusted, how much heat in kilojoules is released? Report your answer to the correct number of significant figures. Okay. So we're going to combust 1 mole. This time we only combusted 0.55 grams, but 1 mole. So let's walk through that. 1 mole of propanol is how much we're going to combust. And where do we go from here? I don't know. But what I do know is that I just found how much heat was produced or released by the burning. How do I know that? Because it's the amount that was absorbed by the water. So I know that the amount of heat absorbed by the water is the same as the amount of heat released by the propanol. And I know that 15.2 kilojoules is released for every, look at the table, 0.55 grams. Okay. So my units don't cancel right now. I have grams, I have moles, those don't cancel out. So all I need to do is be able to get between grams and moles. Well, I know how to do that. The molar mass allows us to convert between grams and moles willy-nilly. So I have to add up all my particles. I have 3 carbons at 12.01 each. 7 and 1 makes 8 hydrogens at 1.01 each. And the 16 grams per 1 oxygen. Add all those up, and you should get 60.09 kilojoules. Sorry, 60.09 grams of propanol. Cross out, cross out, crosses out, crosses out. Leave me with kilojoules. Awesome. Multiply my numbers out. I'm going to get 1,661 kilojoules. Now, sig figs. This problem explicitly told you it's looking for sig figs. They're probably going to give you a point for the sig figs. So let's count them out. The 1 doesn't matter. It's exactly 1 mole, which means it's 1.00000, and it's more relevantly, we're talking about experimental data. Experimental data means you're determined or rounding is based on the experiment. So only numbers from the experiment factor. So the 1 doesn't factor, the 60.09 you got from the periodic table doesn't factor. Only these 2 numbers factor. This one right here on the bottom is 1, 2 sig figs, and up here on the top we have 1, 2, 3 sig figs. When we're multiplying or dividing, the lowest number of sig figs is the one we determine. So in this case, we only care about 2. So 1, 2 sig figs, we're going to cut it here, or round to this decimal spot. So we would say we have 1,700. Be careful you don't put the decimal on. Otherwise, I would say you have 4 sig figs, but you only have 2. If you prefer a little more unambiguous one, go to scientific notation. Put this out and move the decimal 3 spots over. 1.7, and then say times 10, how many spots you moved it over. To the 3rd kilojoule. Either one of these works as an answer. I personally would go with this one just to make sure the sig figs aren't confused or lost anywhere. The zeros always get finicky and a lot of people screw them up. I frequently screw them up, whether or not those zeros are significant or not. But that is B. C. A second student performs the experiment using the same mass of water at the same initial temperature. However, the student uses the alcohol burner containing propanol that is contaminated with water. So there is less propanol per same amount of mass, which is miscible or mixes with propanol. The difference in mass of the alcohol burner before and after the experiment is also 0.55 grams. So this number hasn't changed. With the final temperature of the water in the beaker heated by the alcohol burner in this experiment be greater than, less than, or equal to the final temperature of the water in the first student's experiment? Justify your answer. Okay, there's several ways to go about this. I personally would like to think about it this way. In the first experiment, you are burning 0.55 grams of propanol. In this experiment, you're also burning 0.55 grams, but only part of that is. In this case, you're burning 0.55 grams of propanol and water, which means some of that 0.55 grams is propanol and some of that is water. And even if we take the best case scenario where most of it's propanol, still some of that evaporated or lost mass is water. So, how much? We don't know for sure, but it's going to be some amount. Pick a number. It doesn't particularly matter. If, for instance, we say that 0.50 grams of this is propanol and 0.05 grams is water, we still have less propanol burned. And if that's the case, we release less heat, because based on our calculations we did here, it's 0.55 grams gives us 15.2 kilojoules, but if we only have 0.50, we're going to get less kilojoules of heat released. So that will reduce the amount of heat released, which will reduce our delta T here. If this number is smaller and the mass stays the same and the C stays the same, delta T has to get smaller to compensate. So a way to say this is, because some of the propanol water mixture is water, the mass of the reduced propanol, or the mass of the burner after burning, also includes lost water, which means less propanol was burned. When less propanol is burned, less heat is released to be absorbed by the water, resulting in a lower temperature or a lower delta T of the water. The other possible answer, you could say, because I'm burning things, that water's got to go somewhere. Not all that energy is going to the water. It's going to go into vaporizing the water that's in the sample. And that gets a little messy, but the water in the beaker, the water that we're talking about here, doesn't get all the heat because there's water in the burner. Either explanation is worth 1 point. Let's go ahead and count points. 1 point here, 1 point for the correct answer, 1 point for sig figs, 1 point here, giving you 4 points for the short answer question. And that's 2017 AP Chemistry FRQ number 5. Thanks for watching.